So now let's investigate what this central limit theorem says here. So if you're given random sample of n observations from a population that has mean mu and standard deviation sigma, then when n is big enough, and generally that means n greater than or equal 30, then the sampling distribution of x bar will be approximately normal. And the mean is going to be the mean of the population. Standard deviation will be sigma over root n. So that's the properties we saw in the last example. So the larger the sample size is, the better the normal approximation will be for that sampling distribution of x bar. And that's for any, this is stated for x bar, but usually that's the case for other statistics as well. So larger sample size n means that your sigma x bar is going to be smaller, which means that x bar is going to be a better estimate of the population mean. So central limit theorem says that as sample sizes increase, the sampling distribution becomes more normal. So here's some pictures. So this is sampling distribution of x bar for different parent populations and sample sizes. So here the parent population is just a uniform distribution. And if you look at the sampling distribution for size 2, we get a tent. For size 5, you get something that looks like a normal distribution. For size 30, then you've got a normal distribution with a smaller standard deviation. So here we've got this V-shaped distribution. So samples of size 2, size 5, and size 30. So notice as sample size increases going to the right, you get a more normal, more bell-shaped sampling distribution. And then this is a binomial distribution, severely skewed to the right, samples of size 2, 5, and 30. So notice by the time we get to 30, it's not skewed anymore. And then if you start with a normal population here, then sample sizes are normal for, sampling distributions are normal for all sample sizes. So we can illustrate this by looking at the sampling distribution simulation that we looked at before. So here if we start with a normal population and we take 10,000 samples of size 5, then here's our sampling distribution, normal. Down here, let's go ahead and do our mean, and let's do size 25. So you start with a normal here, and you get normal. So here, normal, but then smaller standard deviation when you've got samples of size 25. So let's look at the uniform distribution. So there's our parent distribution. And again, take repeated samples of size 5 here, and then repeated samples of size 25 here. So we do 100,000 samples of size 5, 100,000 of size 25. So you can see here with n equal 5, this is looking normal after 100,000 samples. Now if we do a smaller sample size, like size 2, we might not be normal. Let's check here. Okay, so approximately normal. Notice how much smaller the standard deviation is here. So how about a skewed distribution? So there's our skewed distribution. So we do 100,000 samples of size 2, and we can see that this is not quite normal. It's still skewed. But when we do samples of size 25, pretty close to a normal distribution. So again, generally, we want sample sizes of at least 30. If your sampling distribution has sample sizes of at least 30, then the sampling distribution will be approximately normal. The reason we want it to be approximately normal is because we know how to do all kinds of probabilities with normal distributions. We can use normal PDF, normal CDF, all the functions on our calculator, and then also a lot of our inferential statistical tests need our sampling distributions to be approximately normal, which requires a large sample size.